All right, I think we're ready to start. Hi, everyone. Once again, my name is Ashley Walker. I am the president and founder of Black and Astro. I'm also a PhD student at Hampton University in the Department of Atmospheric and Planetary Sciences. Today, we are celebrating um, Voices of a Shared Cosmos. The running theme throughout this entire week and today is celestial compositions. Earlier this morning, we had the undergraduate research showcase where they did such an amazing job. And now here we have the graduate research showcase. The graduate research showcase has 11 or 12 amazing students that will be showcasing their research. Many of them may be on the job market coming soon, so you may want to hire them or even just do simple collaborations and write grants with them. So today we will be taking our time out to listen to their research, seeing how cool that they love space and all the amazing things that they do. Without further ado, we're going to go ahead and go to our first presenter. Our first presenter is Kayla McGowan. Go ahead and share your screen, Kayla.
Okay. I just want to double check. You can see it, right?
Correct. Let's
Okay.
go.
Okay. Hi, everyone. My name is Kayla McGowan. I am a fourth year PhD student or candidate, rather, recently at Vanderbilt University, working with Dr. Karen Johnny. And today I will be presenting my work titled Defending the Luck, Quantifying Earthquake Mode Performance in Advanced LIGO. So when most people hear about LIGO, they tend to think about black holes colliding billions of years away or the first direct detection of gravitational waves. But what people don't usually think about is that the one is one of the biggest threats to observing gravitational waves is actually right here on Earth, which are earthquakes. And that's what my project is about. LIGO is one of the most sensitive scientific instruments ever built, ever, and it can detect changes in length that are smaller than 1,000th of the diameter of a proton. So if you put that into perspective, if LIGO were measuring the distance from Earth to the nearest star, it could detect the change about the width of a human hair. So that's very precise. And because it's so sensitive, even tiny motions of the ground can disrupt observations. So my research focuses on understanding how well LIGO's earthquake mode helps the detector survive seismic disturbances and continue observing mode, which is when we're collecting data. And so I'd like to just quickly acknowledge my co-authors as well, Dr. Karen Johnny and Juan Pham, and we'll just go ahead and get started. So before diving into my analysis, I just want to talk about why this problem matters. So LIGO operates in a very delicate state known as lock. And all this means is when the detector is locked, all of the mirrors and the laser systems are precisely controlled. And so this allows us to detect gravitational waves during lock mode or observation mode. But when earthquakes shake the ground enough, it can push the detector out of lock. And when that happens, LIGO loses lock and we're temporarily unable to observe gravitational wave events. So to help prevent this, the detector uses something that we call earthquake mode or EQ mode. And earthquake mode automatically adjusts our control systems to improve the detector's chances of staying locked during earthquakes and different seismic activity. And the challenge that we have is that, we haven't had a systematic way to evaluate how well the earthquake mode is actually working. Historically, studying earthquake mode performance, requires manual review from investigators and noise mitigators like myself, reviewing events one at a time, which is really slow and difficult to scale. So the goal of this project was to create an automated framework that could help us quantify survivability and also give us kind of a data-driven insight to create a data-driven performance plan. So just a fun fact that earthquakes occurring on the other side of the planet can still affect LIGO hours later. So sometimes a detector, like in Louisiana, where I work, for instance, when it, perhaps in Louisiana, it can take maybe a few hours for an earthquake to arrive from like Japan or Chile, but it still affects us even though the energy has dissipated once it arrives. So I just also wanted to give you guys a quick overview. I'm not sure if you can see the pointer, but the plot I have here is just showing the two LIGO detectors. So we have Hanford on the left and Livingston, which is in Louisiana, on the right. And all I wanted to show here is that with the implementation of earthquake mode, especially shown here on the bottom, uh, earthquake mode being in red and then pre-earthquake mode being in blue, the number as well as the energy of the earthquakes that we've survived significantly increased once we applied earthquake mode to each detector. However, you can see at Livingston, um, the survivability isn't as robust as at the Hanford site, which is why I've been doing this study at Livingston. Okay. So, as I stated, to address the challenge, we wanted to create automated earthquake mode evaluation pipeline. So the workflow begins with the detector and the seismic data. We then identify candidate earthquake mode or earthquake episodes, and then we extract the detector behavior during those times, as well as the earthquake's metrics itself using like USGS data and some other accelerometers that we have on site. And then, so then we use this data from the detector and the seismic data. We can then identify those earthquake episodes. And each event is classified in one of two categories. So we either survived it or we lost lock. And then after this classification, we calculate event level and population level statistics. So aggregate statistics about how we're surviving, like daily, weekly, monthly, and most importantly, the threshold that we're surviving. So what is like the maximum amount of energy or the strongest earthquake that we can survive? So those are the metrics that we're mostly interested in. Um, and so the overall goal is to just move from manual inspection to automated. And we want to essentially kind of like create like a report card for earthquake mode and like get an idea of like, how well is it actually performing compared to like what we think it should be performing, instead of asking like, maybe it worked well this time. How is it working across an extended period of time? Because in LIGO, we're constantly doing upgrades. And so whenever we do an upgrade, the profile of the noise changes and the way that the detector responds changes. And so we really need a way to do these quick evaluations, maybe after certain adjustments have been made, or maybe a detector metric has been changed. Okay, so to test the framework, I ran the QuakeBot pipeline, is kind of what I call it, on 2 months of seismic data, and I benchmarked the results against 2 months of handheld labeled earthquake events to ensure that the automated approach was accurate and meaningful. And the pipeline detected more than 200 earthquake events, and for each event, the detector behavior was extracted and classified either as lock, lost, or survived. And then I can computed the survival rates. And this allowed us to compare the characteristics of successful and unsuccessful outcomes. Here on this slide, I have an example of how the earthquake mode works and labels earthquakes. I'm not sure if I'll have a lot of time to get into that, but I'll just quickly go over that. Like in this case, we have a lock loss. And so this drop down means that we're moving into earthquake mode. And then we come up, which means that the earthquake has arrived. And then here we shoot up and we are down. So this would be the duration of time that we survived the earthquake mode. So those are the kind survived while earthquake mode was engaged. And so those are the kind of metrics that we take care of and track. And another, aspect of earthquake mode that we've been considering is that perhaps it's like the engagement time. So earthquake mode doesn't just flip on like a light switch. It takes a bit of time for the detector to implement the robustness changes and allowing the detector to be protected against earthquake mode. And perhaps maybe it's the challenge is that we're taking too long to get to the earthquake mode state. And so we also kind of studied metrics like that. So I'll talk about what we found. So across the data set of 200 earthquake mode events, one encouraging result is that the monthly survival rate increased approximately from like 58% in August to about 65% in September. And that suggests that there may be like meaningful structure and detective performance that we can learn from. We also found that lock loss times were strongly skewed. So, in simple terms, that means that the detector failures don't always happen in the same way, which we expect that there might be multiple reasons why earthquake mode is not performing as well as we think. And also, earthquake mode could not have anything to do with why the detector's not surviving earthquakes. So it could be another issue with suspension or anything else in the detector. But typically in LIGO, we start from the ground up. So they come to, us seismic investigators usually first to determine if it's like earthquakes or other environmental factors. And some of the environmental factors, just fun fact, includes like ground motion from trains. We also get seasonal variation with the waves hitting the shore, also affects how the ground moves. And so there's many, many different areas that you can do, to research why this may be happening. But most importantly, we really just want to understand what is our actual threshold at this moment of of earthquake that we can survive. So like what is the most energy or highest ground motion that we can survive? And um, so we also investigated whether like that threshold might be like separating the survive from the lock loss events. And one of the things that we found is that survivability didn't necessarily have to do with ground motion velocity. So some of the earthquakes that we survived, the ground motion was really high and we wouldn't have expected to survive them, and we did with the earthquake mode, which to me proves that it's working, but maybe just not in every case. And so sometimes we consider the arrival time of the earthquake. So maybe the earthquake is traveled really far away from far away. And so when it arrives, the energy is much lower versus the ones that are closer, and we don't have as much time to prepare, and it hits a lot harder. So a lot of it, I feel like, also could have to do with the variability in the different types of earthquakes we receive and how we receive them. But overall, the earthquake mode is working. It's just not working um, uniformly or reliably in the way that, we would expect or like that we see at Hanford. So what we found here is that approximately 25% of the earthquake or events actually occurred above this threshold. So one out of four earthquakes that we shouldn't have survived, we did. So that's interesting. And that means that, eventually or essentially that, some of the earthquakes like looked really severe, but we survived them. And so while the ground motion is really important, it's not the only factor that drives the detector behavior. And so that was the most interesting thing that I found from the study. And the detector doesn't fail when we pass this threshold, or it doesn't necessarily fail automatically. So its response does depend on a combination of motion severity, timing, and internal detector state. And so, in other words, that means some earthquakes look scary, but they're not fatal. And also, some smaller disturbances can still cause big problems. Okay, so uh, just some major takeaways. So, first, the pipeline provides a fully automated way for us noise investigators to detect and quantify and visualize detector behavior during earthquake events. Second, measuring survival and loss rates gives us a practical framework for evaluating earthquake mode performance. And third, the results suggest here or that there is meaningful structure and survivability that can help guide future threshold tuning. Because ultimately, we do get to decide when earthquake mode engages. And so maybe we should um, lower the threshold or most likely not raise the threshold, but maybe lower the threshold in which we engage earthquake mode. And so it happens automatically, but you also can do it by, using humans. And so we currently have one that's about 400 nanometers per second, and perhaps, maybe we can lower it to 350. You obviously don't want to lower it to like 300 or something too low, because then you become susceptible to things like anthropogenic activity. So that's just like humans on site, buses, we get deliveries, maybe someone drops, I don't know, like a large crate, I don't know. So you don't want to become susceptible to those minor disturbances in the ground. And so you don't want to lower that threshold too low. The threshold that I found using the algorithm was suggested around like 319 nanometers per second, which I still think is just on the lower end. And we would have to um, do a study of more earthquakes, more than just 200, to determine a better threshold for that, and then add in a little bit of human input because you can't, trust the the computer to make all the decisions. So future studies will likely benefit from a combination of motion severity, detector state information, and lock loss timing. Ultimately, this framework could help determine whether the automatic earthquake mode engagement threshold should be lowered, can be lowered. And ultimately, we want to just improve detector resilience and increase our observation time, which we call duty cycle. And but we also, don't want to increase operational risk by, engaging in earthquake mode when we don't need to, because the observations is not as strong. So, if let's say if a gravitational wave comes by in earthquake mode and we detect it, we would not be able to extract as much precise data as we normally could, because the signal would be weaker. And every time that we keep the detector locked, we are preserving valuable observing time that can lead to new gravitational wave discoveries. So ultimately, we want to stay online as much as possible.
Thank you
Um,
so much,
oh,
Kayla, for the presentation.
mhm.
Are there any questions in the chat? Well, not in the chat, in the Q&A. If you have questions, please ask them in the Q&A. Okay, we have a question from John Hood. What is the maximum number of detectors you can lose and still make efficient detections?
Mhm. For LIGO's detectability standard is like we have to have at least two detectors online. And so some of you may know that LIGO is a dual site. It includes Livingston and Hanford, which is Washington and Louisiana. And then we also are part of the LVK collaboration. And so we also sometimes include data from Virgo. Kagra, which is in Japan, used to be another site that we used, but after an earthquake a few years ago, they haven't fully recovered. And so typically the only three detectors that we have are LIGO, Hanford, Livingston, and Virgo, and we need at least two. So if one of the sites goes down, we cannot afford to lose another one.
All right. Thank you so much, Kayla.
Yes.
If you can stick around, if we have more questions, you can answer them in the Q&A.
Yes. So sorry for going over time. Thank you all for listening to me.
Thank you. All right. So our next speaker is Amethyst Barnes. Amethyst Barnes, please come to the stage.
Hello.
All right, let us know when you are ready.
Okay, is that good? Can we full screen it first, actually?
Yes, we can see your.
Perfect. Okay. So, hello, my name is Amethyst Barnes. I am a second year master's student at the CUNY Graduate Center, and my research is on the fate of the stars lying in the hands of the machine, using machine learning to understand star formation rates and cosmological simulations. And my advisor is Dr. Aryeh Mahler. So, star formation rates. What are they? Well, they're just that. They're the rates at which stars form within galaxies. And a key component in star formation is clouds of cold, dense gas. So, if there's an abundance of this cold, dense gas within galaxies, then we know that stars are forming within that. But if there's little to no cold, dense gas, then there's little to no star formation, which is called a quenched galaxy. But with this gas, we are able to observe whether a galaxy is star forming or quenched. So, an example of this is in this plot that was taken using the Spitzer telescope, and it was from a study by Elbaz et al. 2006. And so here we see that there are a scatter of blue galaxies, and they follow this sequence. So we call that the star forming sequence. And so all of the galaxies within that sequence are star forming. But what's interesting is that there's a litter of galaxies on the far right, and are they star forming? Are they quenched? But the interesting question is also if they are quenched, what galaxy properties differ between these star forming and quenched galaxies that make these galaxies quenched? So we can use simulations to try to understand what's really happening because we really don't know, but it is complicated. So, moving on to simulated star formation rates. In these simulations, the stars are formed within this cloud of cold, dense gas. And so we also see this trend of like between the galaxy-wide star formation rate and the properties of other galaxies, galaxy properties. And so for my research, I use Illustrious TNG, which is a series of large cosmological magnetohydrodynamical simulations of galaxy properties. Specifically, I use TNG 100, which looks at 100 megaparsecs of the sky. And within TNG, these are some of the galaxy properties. We have various types of masses. We have different types of half mass radii, some velocity stuff, even masses for the neutral and molecular hydrogen. And then we have some metallicity stuff. So, all that together, the focus of my research is trying to predict star forming and quenched galaxy feature contributions using machine learning. So essentially, what we're looking at is trying to figure out the difference in contribution between galaxy properties for these two types of galaxies. So the main plot of this work is here. So we have the star formation rate against the galaxy stellar mass within TNG. And we see that this trend of this star forming sequence is also shown in here, as we saw in the observed star formation rates. And we also see the little litter of galaxies that we're unsure are star forming or quenched. And so the first step is to make the delineation between star forming and quenched. And so to do that, I utilized the galaxy stellar mass itself, as well as what's known as the specific star formation rate, which is essentially the efficiency of the galaxy-wide star formation rate as a relative to the stellar mass. And so with these cuts here, they're down here, uh, I was able to cut out the star forming region and then the quenched region. And so in total, within TNG, there are 18,831 star forming galaxies and then about 2,796 quenched galaxies. Quenched, we're unsure so far. To dig deeper into the sample selection to looking into this, I chose only central galaxies, which are the galaxies that are in the center of the galaxy clusters, and then also galaxies with a stellar mass that's greater than 10 to the 8.5 solar masses, as well as keeping the TNG galaxy features that are most useful. Because some of the TNG features were like indexing or they were like nan values, so we don't really want to use those. And so, as well as that, at the very bottom of this plot, you see that there are a bunch of very low star forming galaxies. So initially those were at zero, but because we're using logged star formation rates, it's not great to log zeros, and so they were set to the minimum star formation rate within each galaxy. Now, for running the algorithm, I use machine learning and regression models. And so the four types of regression models I used were linear regression, random forest regressor, support vector regressor, and gradient boosting regressor. And then next is to define the targeted features. The target is the star formation rate, and the features, every other galaxy property within TNG that we found would be useful. And then the output is the YPRED, which is the predicted star formation rate, and then the residuals, which is the true minus predicted, and then we have the R2 score, which is the sum of residuals divided by the variance. So these are the first results. At the top left corner, we have the star forming and quenched galaxy regression results. And so the linear regressor is assumes a linear relationship between the target and the features, whereas the support vector, random forest, and gradient boosting, those are more complex, so they can work with nonlinear relationships. So looking at the results for the complex regression models, the scores for the R2 are between zero point 0.8 to 0.9. So it's not bad for both star forming and quenched, like they performed about the same. But the real question is whether the models themselves behave similarly or completely different based on if it's looking at a star forming or a quenched galaxy. And so in order to dive deeper into that, we look into what's called feature importance. So that's essentially tells us how much each galaxy property is contributing to the overall prediction of the star formation rate. And then going into that, I'm using add-on feature importance. So what that does, it finds the single most important feature that adds the most to the R2 score of the overall prediction. And then it adds the next feature on top of that that increases the R2 the most. And then it keeps doing that over and over again until the total R2 score is reached. And so here are the results for that in the bottom right corner for both star forming and quenched. And so we see here that there's definitely a big difference in the contribution that each galaxy property holds for star forming and quenched galaxies. And so this just kind of confirms that the previous plot, the delineation that was made between the quenched and star forming galaxies was needed because they're behaving differently. And so the next part of this is trying to figure out what more can we learn? What more can we learn about the features that are predicting star formation rates? And to do that, we do what's called feature engineering. And that's just what it is. It's engineering new features to then implement into the algorithm. And so the main one that I looked at was surface density, which is the amount of something per area. But if we look at what's called the Kennicutt-Schmidt law, we see that the surface density of the gas affects the rate at which stars form, which is given by this relation here. Here, I got a pointer. And so, because of this relation, we figured that we would learn something new with this implementation. And so, I engineered three new features. So we have the star formation rate surface density, the gas surface density, and the stellar surface density. And so with this, I then, instead of just the star formation rate as a target, I made the star formation rate surface density the target, and then added the gas and stellar surface densities to the feature list. But I omitted the star formation rate and the galaxy stellar mass from the feature list because since they were used to calculate the star formation rate surface density, it would just create like a one-to-one relation, and that just completely not what we want, completely biased. And so the results of that is here, which is it's very interesting because with this Kennicutt-Schmidt law, we assumed that there would be a tight relationship between the star formation rate surface density and the gas surface density. So we thought that the gas surface density would be somewhere in this ranking, but it's not ranked at all. And if we look at the full list of the ranking, it's so far at the bottom of the list, which is very surprising, and we're not sure why. And then another surprising aspect is that the stellar surface density ranked highly for both samples. And so we did expect the stellar surface density to be ranked somewhere like pretty high, but not so much higher than the gas surface density. So the next steps is to really look deeper into why the stellar surface density makes such a significant contribution to the overall prediction. So, in conclusion, there is a distinct difference between the contribution of features towards the prediction of star forming in quenched galaxies. And then on top of that, why does the stellar surface density make such a significant contribution, especially for star forming galaxies? And yeah, that's what I got. Thank you.
Thank you so much, Amethyst. All right, let's go ahead and we know you have a question. All right, you have an anonymous question. In slide 2, wait, I can't. Oh.
2?
I know we're both reading at the same time. But go ahead, you go ahead.
Oh no, I can't see the question. Oh, I see
The
it.
Q&A? Yeah, it's in the corner.
Okay, I see. Okay. In slide 2, why did threshold? Oh, yes, yeah. So with the top bit, the top scatter galaxies, I'm assuming that's what you're talking about. So we weren't sure if those were star forming or quenched just because they're so far out of the sequence of star forming. We just weren't sure what was going on with them. And so we just kind of lumped them into like the quenched region. So at some point later down the line, we do plan on doing analysis on just that little region up here to see what's going on because there's definitely some kind of difference. We're not sure, so we just kind of like lumped it in the quenched for now. Um, but yeah, the threshold was just using the galaxy stellar mass less than 4 times 10 to the 10 um is star forming, and then the other is quenched.
All right. Thank you so much, Amethyst. Again, if you all
Thank
have
you.
questions, feel free to direct them towards the students in the Q&A, and they will type them out and answer them. Thank you again, Amethyst.
Thank
Our
you.
next presenter is Anaya Kaysen, who is also amazing. Anaya, come to the stage. All right, let us know when you're ready.
Awesome. Here. Doop, doop, doop. Can you guys see my screen?
Yes, ma'am.
Awesome. Let me just move this out the way. All right. Hi, everyone. My name is Ayana Kaysen. I'm a second year Fisk Vanderbilt Master's of PhD student, and I'm super excited to talk to you guys about the research that I've done in this program and the research that I will be defending next month for my master's defense. I'm going to talk to you guys about predictive models for binary formation across metallicities and redshift. Okay, so for those of you guys who don't know, gamma ray bursts are the most energetic explosions in the known universe. Here I'm showing you a histogram of the prompt duration of gamma ray bursts with a bimodal distribution, where short gamma ray bursts are the ones that last less than 2 seconds, and long gamma ray bursts are those that last more than 2 seconds. Now, we're going to be thinking in this long gamma ray burst regime where the progenitors of long gamma ray bursts are thought to arise from the collapse of a single massive star. And this is due to its association with its with its supernova counterpart. However, massive stars often occur in binary. So currently in literature, there is work that is thinking, okay, hey, maybe these long gamma ray bursts are also formed in binary systems. So that's where my project comes in. Hernandez et al. 2026 uses MESA code to investigate the initial parameter space that will produce a successful long gamma ray burst, and he finds that the systems with a massive star that is 15 to 25 solar masses and a black hole that is 10 to 15 solar masses can produce a final remnant that has the right amount of angular momentum to produce a jet. So with that, I'm sorry, I forgot to start my timer. Oopsies. So with that, you can kind of think of the black hole as the mechanism that spins up that massive star at the end of its life. So when it produces that jet, it is very energetic and it can create a long gamma ray burst. I was brought into this project to investigate how metallicity influences the rates of these binary systems. And how I did that is I used COSMIC, which stands for Compact Object Synthesis and Monte Carlo Investigation Code. So COSMIC evolves millions of binary stars from their birth properties, and this allows us to be able to track which systems will produce the viable long gamma ray burst progenitors. And so what I did is I ran a suite of binary populations, and I adjusted the metallicity or the amount of heavy elements in each population as I went. And I pressed play on the simulation, and I was able to select the successful binaries that have evolved over the simulation time. And these are going to be the long gamma ray burst progenitors, or just number of binaries. And I divide that by the number of simulated stars. And this gives us fraction of binaries that you're able to basically apply to any type of stellar population. That's why COSMIC is so powerful. And here I am showing you those simulation results where we have absolute metallicity on the x-axis and fraction of binaries on the y-axis. In purple, we have massive star black hole binaries here. And then in cyan, we have binary black holes. And I have this binary black hole rate or fraction on here because I know we have a lot of LVK associates. And a lot of these massive star black holes are binaries are going to evolve to binary black holes too. So that's really good to see that our simulations are consistent with predicting these distributions. But obviously, we see 100 times difference in the fraction of binaries, which tells us that there is a anti-correlation with metallicity and these binary fractions. And this figure essentially answers one of the central questions of my research, which is how does metallicity affect the rates of these binary systems and in turn, long gamma ray bursts. So we're able to use our understanding of metallicity to associate it with a galaxy mass. And then once we're able to get a galaxy mass, we are able to have number of binaries per galactic mass. And if we convolve that with a Schechter function or a galactic density function, we are able to get number of binaries within a volume. This essentially tells us where and when these binaries are forming. And that's what I'm showing you here. We have galaxy mass on the x-axis and then number of binaries per volume on the y. This line right here is redshift of 0 or local universe, quote unquote local for my cosmologists out here. And here we have early universe or redshift about 5. And if you can bring your attention to this blue line, you can see that there's a higher contribution of binaries from the low mass galaxies than, say, in earlier universe. So this is saying, like, although their individual high mass galaxies host maybe more binaries, as you can see, there's a peak here. There is a larger abundance of low mass galaxies due to the galaxy density function, and as a result, this contributes significantly to the overall population. So essentially, just associating metallicity with mass and convoluting it gives us an idea of grants us an idea of where in the universe these binaries are. And in turn, this tells us where we can possibly look look for long gamma ray bursts as well. And that is the biggest takeaway. One of the biggest takeaway in my project is that metallicity is anti-correlated with binaries, and in turn, the formation of long gamma ray burst progenitors. And this emphasizes the need for metallicity-dependent stellar population models and correlation with current population synthesis models like COMPAS or SEVEN. Thank you so much for this opportunity, and I am ready for questions if there are any. Okay.
Thank you so much. And I am so sorry for mispronouncing your name. I know that bothers you, so I have to tell you publicly.
No worries, no worries.
If there are any questions for Ayana, let's see them. Sometimes people got to think about it and then they'll trickle in. Oh, we do have one from Logan White.
Oh, okay.
Yes. So, do you expect to see these progenitors of IGRBs? Look, I don't know these acronyms. To come from primarily pop. Is that 3 stars?
Yeah, pop 3 stars.
Given the metallicity relation you found.
That's a really good question. Especially since we haven't actually seen too many pop 3 stars, I would say that there could be an origin from pop 3 stars. I just think that these are they come from really young metal poor stars. But I try to stay away from saying, oh, pop 3 stars just because we haven't observed them yet. And it's a really big question. So ultimately, when we're looking for these long gamma ray bursts and their correlation with gamma ray bursts, we're more so going to see their remnant as well. So maybe, but that's just because pop 3 stars are kind of a question in itself anyway. So, but thanks for the question, Logan.
All right. Thank you so much, Diana, for your amazing presentation. Next up is Albert Forson. Albert, are you with us?
Yes, that is here. So just a moment to try to share my screen.
Okay.
Okay. Can you see my screen?
No, we can't see your screen at all.
Ah, can you see my screen then?
Yes, go ahead.
Okay, so thank you. My name is Albert Forson from the University of Mauritius, and I present to you on the design and the development of Mauritius Small Array. So basically, why we are doing what we are doing, developing Mauritius Small Array. It's a prototype instrument for in Africa as part of a square kilometer array project in Africa based in Mauritius, the Indian Ocean island, as you can see from here. And this work is probably to study galactic H1 hydrogen. And also one of the work is also to provide a very close short baseline interferometry instrument as a prototype to be able to have a skill development in Africa as well towards the square kilometer array work in Mauritius. So this is the engineering framework where basically the region is known for its cyclonic situations. It's very intense, and cyclone in the past record can go about 260 kilometers per hour. That was the model that we started with. So the design started with the analysis, taking in the data from the previous cyclone record and other environmental conditions into that design. So comes down to the structure design to be able to meet that standard or able to meet any future cyclone situation. Then we move down to the numerical simulations where we simulate this through the CAD 3D and be able to do other simulations on the structure analysis and see whether this will be able to meet that standardization then throughout the development. Here is the 3D modeling and the verification analysis where we did the 3D because we have this parabolic dish as a legacy dish from telecommunication company, which are originally not known for radio astronomy, but through the project, the vision is to be able to re-engineer this parabolic dish. So these are the redesigning that were made throughout this process. So then we come to our grid analysis through all the simulation as base engineering simulations. Now, whether this system or this design will be able to meet all the environmental conditions in the future, or also be able to meet the standard of radio astronomy at the same time. So these are the static structure analysis that we have put through and be able to inject into the system from 260 kilometers per hour wind speed and be able to analyze what are the structure defects that this instrument or system will be able to withstand. And these are the good results that shows throughout the analysis. Once these simulations go through or is successfully through, we then move on to the fabrication or the design implementation of that system. So from here, you can see this is where the columns fabrication begin. So we went through the step-by-step fabrication and welding process because all of this has gone through the design analysis procedures. Then the dish, as got from telecommunication company, also has to go through the same and have to do a lot of refabrication and welding iteration from point to point before you'll be able to make that stage. From that stage, we move through the civil as the concrete analysis or the concrete platform design and development. This has to also meet that particular standard that in terms of any high cyclone on a wheel, it's unable to topple over and uproot. So also have to go to a rigorous design and implementation. So from step 1 through 3, this is what it looks like at the time. Then we move to step 6, also have to redesign a feed system that will be able to meet all this situation in that particular environment. At the end of the day, we're able to build up our 4-element interferometer, and this is the final result as you see in step 7. So here, this is the particular motor or tracking system we design and use. These are the stage in which we are doing the most of the test trial between the point to point. And this is our control station where we'll be able to configure and control all the system through the system and be able to issue one control program and be able to track all the antennas to all astronomical destination and location that you want for any selected celestial observation. So far, these are the observations or measurements so far we've made through our wideband and autocorrelation, we're able to autocorrelate all the 4 antennas successfully, meaning that all of them are receiving same input, responding to the same signal. And as you see, these are the measures visibility phase demonstrating the characteristic periodic wrapping associated with coherent interferometric response from the observation of the sun. And the same also here, you can see the normalized visibility coherence as a function of the relative solar angle. We move through that process also have a few H1 observation through that, and these are the plots per each antenna. So the state in which we are now trying to do a few calibrations and now be able to get other imaging stability. This is also same part of pointing all the doing the transit measurement of the 4 elements interferometry. Yeah. So in conclusion of what we have done so far, we are able to validate the engineering of this particular project, and as a robust, environmentally resilient system in that region throughout the period that this system was developed. We were able to face about 7 series of cyclone, which highest rates from around 105 kilometers per hour. After post-cyclone analysis, we realized that the system is responding accurately, perfectly to the design situations. So the capacity building in terms of how astronomy counts in Africa, in the region as well, also has been met in terms of that, because this was designed from the scratch to the end. And we hope that the SKE project will now have a model that will be able to build on the future square kilometer array project as well. So the small Mauritian array demonstrated as a locally developed engineering solution that can support the next generation of radio astronomy and strengthen Africa's scientific capacity, and also provide a pathway towards a future participating in the African VLBI network and square kilometer arrays. And also these are the advices. And thank you. And any further question, I will come.
All right, thank you so much, Albert. Do we have any questions? Okay, we do have a question in the comment. In the Q&A. It says, if a big worry is strong winds, why not use a modified version of the quote unquote Christmas tree design as the MWA in northern West Australia?
Okay, so thank you for the question. If I get the question, so I think this situation in terms of this region also has its own peculiar environmental conditions, its cyclones. It could be those one in Australia have their peculiar environmental condition. And moreover, Africa is hosting the mid-frequency square kilometer array project. And this region needed to have one of the square kilometer station in this region. So the antennas must be developed in this environment to meet the specific region conditions. But if you adopt that one from Australia, may not perfectly work for the one in Mauritius or Africa. Australia is hosting the low mid-frequency. So their design also is a bit different from the one Africa is holding, which is the mid-frequency. That is why we are having this reflector aperture from the Christmas tree design from SK.
All right, thank you so much, Albert. Next up, we have Jasmine Freeman. Please come to the stage.
Hi. Let me share my screen. Do you see my screen?
Yes, ma'am. Go ahead. Take it away.
Awesome. So, hi, everyone. My name is Jasmine Freeman. I'm currently a second-year PhD student at the University of Georgia, and I'm going to be talking about my research on exoplanet detection using data from NASA's Transiting Exoplanet Survey satellite. So, briefly, what is TESS? So, TESS is a NASA space telescope that was launched in 2018 to search for planets orbiting stars outside of our solar system. It does this using the transit method, where a planet passes in front of its host star and blocks a small amount of light. And this creates a small dip in this brightness that we can detect. And so for this research, I analyzed observations from TESS sector 59. After signals are detected, they're placed in different tiers. So tier 1 has the most promising results, with tier 2 having the uncertain signals that require further investigation, and tier 3 has signals that are likely not exoplanets. And so the challenge is determining which signals are real planets and which ones are false positives. And so to do this, TESS data goes through a series of processing steps. And so for the first one is compute optimal aperture, and it identifies the best pixels to use when measuring light from a star while minimizing contamination from nearby stars. And the second one, photometric analysis, it measures how the brightness of the star changes over time, and it produces what we call a light curve. And so for the third one, pre-search data conditioning, what it does is it removes instrumental effects and systematic noise that could interfere with the detection. And so transiting planet search, it looks for repeating dips in brightness that may indicate a planet crossing in front of the host star. And then last but not least, we have data validation, which is where majority of my research take place. It tests whether the signal is likely to be a genuine planet candidate or a false positive. And so one of the biggest challenges in exoplanet detection is separating real planetary signals from noise. And so to do this, astronomers use two important measurements. We have the multiple event statistic, or the MES, and the signal to noise ratio, SNR. So with the MES, it measures how strongly a repeating transit signal matches the pattern that we would expect from a planet passing in front of its host star multiple times. So in simpler terms, it combines information from multiple transit events to determine how convincing the detection is. And so a higher MES value means we have stronger evidence that the signal is real and not simply random fluctuations in the data. And with the SNR, it just tells us how clearly a signal stands out from background noise. A higher SNR means we can be more confident that the signal is real. And so for the examples that we have, it shows the difference between low quality and high quality signals. So on the left here, the transit events are much more consistent and they stand out clearly from the background noise. And that leads to a higher MES and SNR values. We also see that the flux is very consistent as well, which is a good sign. And then, on the right, the light curve is noisy, and that makes it difficult to distinguish a clear transit pattern. And so this tells us that it might not be what we are looking for. And so with these together, we identified those candidates and reduced the number of false positives that require follow-up investigation. Even when we detect a transit signal, we still need to verify that the signal is actually coming from the target star and not from another nearby star in the field. And so in these images, the red star represents the target star that we are investigating, while the blue stars here represent some neighboring stars that could potentially contaminate the observation. And the cross in the middle is the measured location of the transit signal, and the surrounding circle region here is the uncertainty in that measurement. So in the good example, the measured transit signal is centered on or like very close to the target star. And so that tells us that the dimming event is occurring on the star we intended to observe, which makes it a very strong candidate. And then in the bad example, of course, the measured signal is offset from the target star and appears to be very close to the neighboring star. And so it tells us that the dimming may actually be originating from the nearby star rather than the target itself, which makes the signal more likely to be a false positive. And so all in all, centroid analysis is one of the most important validation tools because it helps us to determine where the signal is coming from, and it increases our confidence that a candidate is truly an exoplanet. So using these techniques and all of the tens of thousands that were in each tier, our analysis identified 11 new potential exoplanet candidates across all of these sectors. And so these represent some exciting opportunities for future study and follow-up investigations. So our next step is to examine additional test sectors and data sets to determine whether these signals appear consistently over time. If the evidence continues to support these detections, we can publish them as community targets of interest, which allows astronomers all around the world to perform follow-up observations with their ground-based telescopes. And so ultimately, this work that was done at the SETI Institute contributes to the broader search for planets beyond our solar system and helps us better understand the diversity of worlds that exist throughout our galaxy. Thank you.
All right. Thank you so much, Jasmine. All right, let's see if we have a question in the Q&A. All right, we have one question from Dr. Anaya Relaford. How much time do you need to demonstrate consistency of the 11 that you found?
How much time do I need to demonstrate a consistency?
Yes,
That was
of the 11 potential exoplanets that you found.
At first glance, it may sound like it doesn't take a lot of time to demonstrate any consistency. However, we have to go through extra validation for the light curves to be properly consistent, not to mention go through the data sets that's already published that may contain the 11 that we found. So it does take a pretty long time before we can actually confirm it to be exoplanets.
All right. Thank you so much, Jasmine. So we're going to go to our next presenter, Marcel Howard.
Hopefully you guys can see my screen.
Yes, we can.
Okay.
Take it away.
All right, perfect. So first of all, my name is Marcel Howard. I'm a PhD candidate at the University of Pittsburgh. And broadly speaking, my PhD is focused on studying particle physics and strong gravitational systems. And here you're going to see a particular project that I've been working on roughly for the last year or so. So we probably all have heard of dark matter. At the very least, we have a passing familiarity with it. Dark matter is just responsible for holding galaxies such as ours together. Now, one of the mysteries of dark matter is how exactly did it even get here? Which is to say, like, what is responsible for producing the dark matter in the first place? Uh, Starting from the 1980s and up until maybe within the last 10 years, the prevailing narrative that we had for producing dark matter in the early universe is that it was a class of weakly interacting massive particles called WIMPs. WIMPs were a result of this framework for describing a possible symmetry of nature called supersymmetry. And the really nice thing about this framework is that it actually gave us a very natural dark matter candidate that had all the properties that you would want in a dark matter candidate. And it would solve a lot of problems, a lot of technical issues associated with the standard model. Problem is, if those particles were real, then we probably would have seen them in the LHC by now. So this is actually have inspired theorists to look for these, so-called more exotic scenarios of producing dark matter. And here I'm going to focus on a particular way of doing that, and that's via the expansion of space. So we're probably all somewhat familiar with quantum mechanics, or at the very least, we have a passing familiarity with the uncertainty principle. The uncertainty principle tells us that if you were to zoom in on any region of space, what you would find is that that region actually is not empty. You actually have a constant stream of particles popping in and out of existence. But we have to remember that those particles that are popping in and out of existence, they are doing so in the context of an expanding universe. So you can imagine a scenario where I pop two particles into existence, such as what you see on the screen right here. And right before those particles have a chance to annihilate with one another, the space in between those particles expands incredibly rapidly. So you might ask yourself, well, was there actually a period in the universe's history where we had this very rapid expansion where you can produce particles? And the answer is that we actually basically think yes, that in the very earliest moments of the universe's history, the universe actually went through a period of a very rapid exponential expansion that we call inflation. And so some of my colleagues, they took some of these observations, and then they asked the question, can this gravitational particle production be responsible for producing all the dark matter in the universe? So just to be a little more explicit as to what exactly we assume about those dark matter particles, we assume that they are something called a spectator particles. That's just a fancy way of saying that they exist in the very early universe, but they don't contribute a meaningful amount to the expansion of space. They also assume that the particles, when they're produced, they just sit there. They are what we call free. And lastly, we assume that the universe started off as some, rapid expansion of space, but it very quickly transitioned to a state of very hot, dense particles. And I should mention that HI is basically how energetic this exponential expansion was. And so when my colleagues ask, okay, with all these actually fairly minimal assumptions, can we produce all the dark matter from just the expansion of the universe? And in fact, the answer is actually incredibly yes. So on this plot, what you're seeing here on the horizontal axis is the mass of the particles that you produce in these funny little particle physics units that we call electron volts. And on the vertical axis is the relative fraction of the particles that you produce versus the amount of dark matter in the early universe. And you can see right here, there's this nice little sweet spot. If I fix how energetic that early period of rapid expansion was, there's a sweet spot right in between where you get all of your dark matter. So this is interesting for a couple of different reasons. First, if you think your dark matter are axions and you have some production mechanism, well, first of all, you might notice that this mass is actually pretty close to what you would expect the typical axion mass to be, which means if you have a method to produce axionic dark matter, then you necessarily need to take this gravitational particle production into account. Now, you may have also noticed, as I mentioned frequently, is that there's this sweet spot, so this very particular mass that you can produce these particles, and so you might worry about things like fine-tuning of the model. And so this is where my project comes in, where I'm basically repeating the same, taking the exact same assumptions from the previous calculation. And now I'm going to allow the dark matter particles to talk to each other, or what we say to interact in particle physics land. I'm talking about a self-interacting dark matter. So why would you even care about this? Well, I would argue, first of all, it's still actually a viable model for dark matter. And in the next slide, I will show you what exactly that means. I would also argue that this is the most minimal thing that you can do to dark matter, where it's not, just a totally boring thing that just sits in space and it does literally nothing else. And another feature when we allow these dark matter particles to talk to each other is that we can potentially expand which viable masses there are for dark matter, at least for this production mechanism. So here's a plot that I have on the available, what we call parameter space for viable self-interacting dark matter models. And you can ask me at the end of this talk what exactly these different constraints mean. The most important takeaway from this plot is that the colored regions represent not viable dark matter models. So if you pick a mass and you pick a what we call a coupling, or this number determines how strong the dark matter particles interact with one another. So if you pick two numbers and you fall in the shaded regions, then that means that dark matter candidate is not viable at all. And so the only viable region is the region that is totally unshaded. Now, when we allow these particles to talk to one another, what we get is this interesting phenomenon that's known in the literature as parametric resonance. So the way to think about parametric resonance is the following. So we're probably all familiar with the simple harmonic oscillator, but when we learn about the harmonic oscillator in our classes, we are taught that the frequency is just a constant. But here, parametric resonance is what happens when the frequency of your harmonic oscillator is also allowed to oscillate periodically. So the way that you can think of this within the context of this model is that I have my dark matter particles. They are oscillating back and forth, right? But now, which wasn't a feature in the previous model, because these dark matter particles can talk to one another, now you can kind of think of it as they can oscillate in phase with one another. And when they oscillate in phase with one another, what happens is that you actually end up in a resonance between these different particles. In fact, and when you end up with this resonance, you actually excite the vacuum. And when you excite the vacuum tries to de-excite itself by producing extra particles. So we actually get two production mechanisms for generating dark matter for the price of one. Not only do we get dark matter from the expansion of space, by the dark matter particles talking to one another, they too can produce their own sort of dark matter. And so here's an example plot that I made of on the vertical axis is the number density, so number per volume. And on the horizontal axis is the momentum at which you produce those particles at. So lambda equals 0, that's just the case where the particles don't talk to one another. And lambda is 10 to the minus 3. So for this choice of parameters, this is you can see that you actually get the number density actually visibly change. In fact, these extra bumps that you see here, these are actually the different resonances that you excite these particles. So I am absolutely out of time. So with that being said, I will end it right here. And thanks for listening to me.
Thank you so much, Marcel. Do we have a question in the Q&A? All right, we're gonna move forward. If there are any questions, feel free. The panelists will answer them. They will type them in the Q&A. Thank you so much, Marcel. Our next presenter is Sabrina Khan. Please come to the stage, Sabrina.
All right, give me 1 second. Okay, hopefully you can all see that.
Yes, we can see it. Take it away.
All right, good afternoon, everyone. My name is Sabrina Khan. I am a planetary geologist at Johns Hopkins University, and today I'd like to introduce you to some of my favorite features on the Martian surface, starting with one that I'm sure you're already familiar with, which is Olympus Mons, the biggest volcano not only on Mars, but in the entire solar system. And because it's so big, most people think it erupts in these giant, cataclysmic, Pompeii-style eruptions that blot out the sky and wreak death and destruction upon all the little Martians around. But I'm going to tell you that this volcano, as far as we know, is kind of a gentle giant. And the reason for this is that there are a few different kinds of volcanism that operate on planets. Some volcanoes act like Pompeii, but other volcanoes act like the ones in Hawaii. Now, if you're lucky enough to have ever lived or vacationed in Hawaii, then you might recall that the eruptions there tend to be kind of gentle. The lava is kind of like a thin soup. It flows and flows over long distances, and this is because the composition of the lava is basaltic. So it tends to have a lot of iron and magnesium, which makes it a very low viscosity kind of lava. So when that basaltic magma accumulates in the magma chamber of a volcano, any pockets of gas that are accumulating there can rise really easily through that low viscosity fluid and escape into the air. And since there's no buildup of pressure, that lava kind of just spurts out and then dribbles all over the surface in a relatively safe eruption. And we see this kind of volcanism in Hawaii, in Iceland, many other places on Earth, but this also is exactly the kind of eruption we think Olympus Mons produced. And those basaltic lavas are believed to have flowed all over the Martian hemisphere, the Martian northern hemisphere, where, as you'll see in a minute, the terrain has been completely smoothed out as a result. But the other kind of eruption we could get is more like Pompeii. I don't think I have to explain how deadly this one is, but the reason it's so deadly is because the magma involved here is more felsic, so it has more silica. And that silica makes the magma really sticky and goopy, and it allows pressure to build up really, really fast, leading to a far more explosive kind of eruption. And when that eruption does happen, there are a few other important consequences. First, a plume is generated. So hot volcanic gases are rising really rapidly up into the atmosphere, bringing ash and other debris with them. And when that plume collapses, all of that hot gas and debris go tumbling down the flank of a volcano very, very quickly. And that is called a pyroclastic flow. So this is the thing that killed everybody in Pompeii. The second thing that happens is that all that dust and ash that gets caught up in the atmosphere begins to fall out. And this is called pyroclastic ash fall. And it can extend hundreds and thousands of kilometers away from the source vent, ferried away by things like the wind and other forces. Now, the critical takeaway here is that, while we have seen and experienced this kind of volcanism all over Earth, we have no idea if this ever happened on Mars, which is kind of wild because it's actually more favorable on Mars than it is on Earth, and I would love for someone to ask me why that is in the Q&A. But suffice it to say that we have looked and looked all over the Martian surface, and we just can't make a compelling argument that this ever happened on Mars. Until, of course, we discovered my favorite unit and the center of my life for the last 4 years, which is the Medusa Fossae Formation. So now you all know where Olympus Mons is, but if you pan a little bit to the west, you'll discover a region that's pretty notable for a few other reasons. First of all, there are a bunch of volcanoes in this area, Olympus Mons, of course, but also Elysium Mons and Apollinaris Mons, lots of Monses. You'll also notice that there is an abrupt change in elevation. So this is called the Martian crustal dichotomy boundary. It roughly occurs along the equator. And it distinguishes the older, heavily cratered terrain in the south from the much younger, smoother terrain in the north, which we interpret to be the result of those Hawaiian style lava flows that I was just talking about. And of course, we have a few robotic friends in the area, namely Spirit and Curiosity, RIP Spirit. But the real highlight of this region is the enormous deposit of material that we like to call the Medusa Fossae Formation that's outlined here in black. Now, it's made up of these 5 exposures that span approximately a quarter of Mars's equator, which is absolutely insane. And it takes up an area equivalent to the size of Greenland, which is crazy because that's about like 2.1 million square kilometers. It's massive. And the reason that I'm studying it is because up until recently, we haven't really been able to figure out how the MFF, the Medusa Fossae Formation, formed. We have all of these theories, a lot of really wacky theories. Someone should also ask me about that. But there's one thing that's becoming more and more apparent is that the Medusa Fossae Formation might be the product of ash fallout from an explosive Pompeii-style eruption on the Martian surface. And now I'm going to tell you how we came to that conclusion. So let's return to our frontier on Mars, who's about to be taken out by a hot stream of hot volcanic gases and debris that make up our pyroclastic flow. So these flows can climb up hills no problem, but eventually they're going to run out of steam and start to tail off. So once our friend has been hit by this flow, he'll also get buried by all that volcanic ash that's falling out of the atmosphere. Now, this kind of eruption event can happen like multiple times, and you'll start to accumulate these layers of flow and ash deposits, which will represent like a layer in the geologic record. And these deposits will have 3 key properties. First of all, the deposits will be layered, with each layer representing 1 or more eruption events. Those layers will also begin to thin as you move further and further away from the source vent, as the energy required to transport those sediments begins to dissipate. And then those layers will also drape over whatever terrain existed there before. So the orientation will mimic and eventually dampen any hills or basins that were in the pre-existing terrain. And all of those features are the things that we looked for when we began our exploration of the Medusa Fossae Formation, and this is what we found. So we decided to focus only on that central portion of the Medusa Fossae, which you saw an outline of. This is called Lucus Planum. And we started by plotting every location where we saw a layer. So in this first column here, you can see immediately that we found a lot of layers marked by those little black dots. And so we've met that first bit of criteria. We can also tell from this figure that those layers tend to show up primarily in the western half of this unit, this Lucus Planum bit, rather than the eastern half. And this is interesting because the loss of layer visibility could happen if the layers were getting thinner and thinner as you move towards the east, to the point where you can no longer resolve them in our imagery. So that leads us to our second bit of criteria, which is thinning with distance from whatever source vent there is. And after measuring all of the layers that I plotted in that first plot, we can capture the thickness of each of those layers, and we find that the layers are thickest in the western part of Lucus Planum and thinner as you move towards the east, which you can see in this central figure, which shows an output of what's called a Kriging model, which is a tool that performs like spatial interpolations. So from this plot, you can see in the dark orange, those are where our layers are thickest, and the lighter orange is where our layers are beginning to thin out. So criteria 1 and 2, check and check. And finally, we want to determine whether or not the layers are draped over the terrain. And this can be really tricky if you can't see where the underlying terrain is in the first place. Fortunately, there are a few spots in the Medusa Fossae where we can actually see impacts, which are associated, or impact craters, which are associated with impact events. And we know, of course, that the terrain there is going to be a bowl. It's going to be like a little impact basin. And so I want you to think about this like you're filling up a bowl with fondue, with layers and layers of fondue. The more, as you fill in one layer, the fondue sticks to the sides of the bowl, fills it up a little, and then hardens. And the more and more layers you add, the more the bowl fills up until the top is perfectly flat. So this is the draping and dampening effect that I was referring to earlier. And if you were to go in and measure the angle of each layer of fondue relative to the sides of the bowls, what you would see is that it goes from really steep towards the side of the bowl to really shallow as you move inward. And that's exactly what we see when we look at the layers in the Medusa fossae in this particular basin. So you can see here that on the right-hand side in this column, that as you fill the basin, each layer becomes shallower and shallower, 1, 2, 3, 4, as you go in towards the center of the basin. And so this is like the final nail in the coffin. Once our layers are draping the terrain exactly the way we would expect in a volcanic scenario, and based on all of this, we can confidently say with some certainty for the first time that there is evidence of explosive Pompeii-style volcanism having occurred on the Martian surface, and that we can trace the source vent to a nearby volcano called Apollinaris Patera. So I want to thank everybody who has helped me complete this work, from my advisor to my collaborators at NAU and SETI and APL, and I would love to hear any questions you have. Thank you.
All right, thank you so much, Sabrina. So let's see. We do have a question. It's an anonymous attendee who asks, why is Pompeii-like eruptions more viable on Mars?
Yes, thank you for asking that question. So the reason that it's more viable on Mars is because the pressure on Mars is so much lower than it is on Earth. So Earth is 1,000 millibar atmospheric pressure. On Mars, the pressure is about 6 millibar. So it's very, very minimal in comparison. So the amount of pressure that you need to build up in a volcanic chamber is that factor smaller on Mars than it is compared to Earth. And just a little bit of pressure buildup will allow you to produce a really explosive eruption. So even basaltic eruptions, theoretically, on Mars should be able to produce a really explosive style of eruption, which is why it's really fascinating that we haven't seen it. I hope that answers your question.
All right. Once again, thank you so much, Sabrina. Again, the students are able to answer questions within the Q&A if you ask them. All right, next up is Savaria Parrish. Please come to the stage.
All righty. And here we go.
Wait a minute, we can't see your screen for a minute.
All righty.
Now you can go.
Gotcha. So hi, everyone. My name is Savaria Parrish. I'm a rising first-year PhD student at the University of Alabama, Huntsville. And today I will be presenting my work on characterizing the atmospheres of LT transition brown dwarfs using the Sonora Diamondback models. I did this work in collaboration with the Brown Dwarfs in New York City Research Group, which is housed at the American Museum of Natural History. Additionally, my advisors who helped guide me through this project were Dr. Jackie Faraday and Dr. Genaro Suarez. Let's see. I first want to start off with saying what a brown dwarf is. So a brown dwarf is what we call a failed star. Essentially, it forms kind of similar to a star in the sense that there is a giant gas molecular cloud. Enough mass occurs to where it collapses in on itself. And when it collapses in, a protostar starts to form. Essentially, what differentiates a brown dwarf from a regular star is the mass. Brown dwarfs typically don't have enough mass to start nuclear fusion or fuse hydrogen as we see in regular stars. Essentially, they are between 13 to 75 Jupiter masses, and anything above the 75 Jupiter masses will typically get you a nuclear fusion burning star. And so in the case of brown dwarfs, because they don't get that big, they tend to slowly contract and cool, and now we have a brown dwarf. And brown dwarfs are classified into different spectral systems. Essentially, there is the L-type, the T-type, and the Y-type brown dwarf. An L-type brown dwarf is a little bit hotter than a typical T-type brown dwarf. And so an L-type brown dwarf is between 1,300 to 2,000 degrees Kelvin, while a T-type brown dwarf is between 600 to 1,300 degrees Kelvin. Essentially, what my project tries to study is that transition between an L-type to a T-type brown dwarf. Specifically, as we get more and more into it, they're subdivided into 9 subdivisions. Essentially, each subdivision has specific spectral features that we tend to see. My project focuses on late L-type brown dwarfs, so L8 to L9, and early P-type brown dwarfs, so T1 to T2. Onto the observational data side for what I did. And so I used the brown dwarf binary system WISE 1049AB for my study. Essentially, it is the closest brown dwarf binary system to us at only 2 parsecs away. Essentially, it is the perfect component for studying that LT transition because the A component is an L8 or late L type brown dwarf at 1300 degrees Kelvin, and the B type brown dwarf is an early T type brown dwarf at 1100 degrees Kelvin. And so I'd be studying those transitional differences between the two. And because they're a binary system, they formed in the same molecular glass cloud. And so they should have roughly the same not temperatures, but roughly the same spectral features. And so we use the data from the James Webb Space Telescope to collect this, and we collected spectra. Spectra is the light we collect from celestial objects, and it can reveal the composition, temperature, density, mass, and even velocity of the celestial objects that we tend to observe. Over in figure 1, I have a labeled spectral energy distribution graph, and essentially this is the spectra that we plotted. So on the left, we have the A-type brown dwarf, and I highlighted some of these spectral features and the molecules that we see in the spectra to kind of show you how we are revealing the composition from the brown dwarfs. And over to the right, I have the spectral energy distribution of the B-type brown dwarf. And here I've circled some of the differences that we can see as you go from an A-type and L-type brown dwarf to the T-type brown dwarf or the B brown dwarf. And so you can see stronger absorption lines. You can also see that there are some features that get muted. And from what we learned in an L-type brown dwarf, you have sediment clouds that are going to be observable from the telescope, but as you get colder, those sediment clouds tend to sink. And so in the T-type brown dwarf, you don't see that as much, which is highlighted here. And so onto the Sonora Diamondback model part of my project. Essentially, what I wanted to do was to compare our observations from the James Webb Space Telescope to synthetic spectra, with the overall goal of finding the best fit synthetic spectra for our observations. I used the Sonora Diamondback because it is the newest and most up-to-date cloudy atmosphere models that we have. Essentially, there's over 30,000 spectral energy distribution graphs in the Sonora Diamondback models. And so what it is there's 30,000 combinations of temperature, surface gravity, metallicity, and FZ values. And over here pictured in this middle graph, I have a whole bunch of example synthetic spectra plotted with different temperatures, different cloudiness, to kind of show you what that would look like. And so for the FZ parameter, this is how fast clouds settle. And essentially, if you have a low parameter between 1 to 3, the clouds will stay high in the atmosphere and be able to be reproduced and seen in the spectra. Versus if you have a high FZ parameter, you have larger particles which settle more quickly. And I also have surface gravity. And so this is how hard gravity pulls on its atmosphere. So if you have a low surface gravity, you tend to have puffy planets versus a high surface gravity, you have more compact planets. And metallicity just refers to the amount of metals heavier than hydrogen and helium that's observed in the atmosphere. So between negative 0.5 to positive 0.5, you'll get subsolar, solar, or supersolar. And in order to do these comparisons between the synthetic spectra and the actual observations, I used a program called the Spectral Energy Distribution Analyzer, or SEDA, which was created by Dr. Genaro Suarez. Essentially, it uses the chi-squared statistical analysis to do this. And what that means is it overlays the observations to each of the 30,000 synthetic spectral models, and whichever one comes back with the least amount of error between the data points is what we call the best fit synthetic spectra. And so on to my results. I found that with doing this, the Sonora Diamondback models capture the overall fit of our observations, but they fail to reproduce the observations at 2 to 4 and 8 to 12 microns. Essentially, what's represented here in this graph is we have our actual observations of each component in blue, and then we have what we found is the best fit synthetic spectral model from the Sonora Diamondback models in orange. And so as you can see, they fit the overall shape, but specifically in specific regions, we don't really see the orange matching our observations. And essentially, it also told us that the best fit synthetic spectral model was 1,000 degrees with a gravity of 1,000 and an F-set parameter of 4 for the A-type brown dwarf. But then for the B-type brown dwarf, it said the best fit was 1,100 degrees with a gravity of 3,160 and an F-set parameter of 8. Now, this really shouldn't be because they formed in the same molecular cloud, and so they should be roughly similar. And so this shows us that we still need to work on our models if this is the best fit that we can get. And so for future work, we're going to try to constrain and add silicate cloud grains into the Sonora Diamondback grid to kind of account for the differences in the spectral shape of the 8 to 12 micron region. And so thank you guys so much for listening to me, and I am free to take questions.
All right, thank you so much, Savaria. Do we have any questions in the Q&A? All right, we don't have any questions, but feel free to ask her any questions offline or in the chat, in the Q&A. So our next presenter is Sean Ray.
You see my slides?
Yes, we can see your slides.
Okay, perfect.
All right.
Okay, I'm ready. Hi, everyone. My name is Sean Ray. I'm a second-year master's student at the CUNY Grad Center, working with my advisors, Barry McKernan and Slavik Ford. And I also worked with a postdoc named Keith Mittman, who was a big help on this project. And so today we're going to be talking about considering numerical relativity for upgrades in McFax merger dynamics. And so, and I'll get a little bit into what McFax means in a second. But to start off, I first want to give a background in gravitational waves. So to start out with, we have two black holes that are merging that are producing gravitational waves, which are just ripples in space-time. And so I'm going to freeze the movie right as these two black holes merge, and then match a what's called a strain graph. So this is just those ripples in space-time matched with the strain data that we receive on gravitational wave detectors. And so whenever this is generated from a black hole merger, it travels across the universe and hits our detectors here on Earth. And so we have some, as we've heard before, we have some in Washington, Louisiana, in Japan, and in Europe. And so whenever these detectors flag a black hole merger, they're telling us where that a black hole merger occurred. But the problem is we don't really know where these black holes are coming from. And so here is a figure of just a general galaxy. And so we can see we have galactic halo, globular clusters, the general disk, the galactic center. And so if we take that frame from before, so our two black holes that are merging, there are three possible regions or locations that that these black holes can merge, and these locations are what we call channels in the gravitational wave space. And so the first one is isolated binaries. It can just be a binary black hole within the disk of the galaxy anywhere, that from two dead stars from maybe a star forming region or just in a random point in space. But the second is globular clusters. And so these are very high density regions of space where there are millions of objects per cubic parsec. And the third region that I'm going to be talking about and focusing on is the galactic center. And so specifically, galactic sensors that are active are called AGN. And so in MCFACS, which stands for Monte Carlo for AGN Channel Testing and Simulation, we simulate black hole mergers, binary black hole mergers inside of AGN. And so to start off with, I have a little GIF here showing the different types of eccentricities. And so when you have a low eccentricity, you have what's called a circular orbit, which is shown in red, and then a very high eccentric orbit, which is in pink. And so our black holes that we make in MCFACS start off as this high eccentricity orbits. And then as they interact with the gas in the middle of the galaxy, in the middle of an AGN, their orbits begin to circularize. And so as they're circularized, then they're primed and ready to become like essentially eligible to merge with other black holes in the disk. And so whenever these black holes are merged, or whenever they meet and form binaries, they can either soften, which just means to grow farther apart, or harden, which is to get closer together in their orbit. And so once these black holes merge, they produce a kick velocity. And so here is just a little drawing of an AGN disk. And so the orange yellow is just the gas in the disk. And you can see that we have different populations of black holes orbiting this AGN disk. And so one of the neat things one of the things about MCFACS is that we actually didn't previously treat black hole mergers with numerical relativity. We just used simple analytical models. And so my project was implementing a surrogate model, which you can see in the video on the right, is taking fully solved numerical solutions, which are very expensive, and then interpolating over those solutions to get an arbitrary, ambiguous calculation of black hole mergers. And so we can calculate the mass, the spins, and the kick velocities of any black hole merger that's within a certain range without having to run these incredibly computationally intensive models, and saving us on computational time. And so my project was implementing this surrogate into MCFACS. And a little, also a little video, you can see that NRSIR, which is the software that I use, produces is that we have two orbiting black holes. And so they take all the parameters of the black holes, the spin orientations, the angles, the orbital angular momentum, and then puts them all together to really most physically accurately simulate these black hole mergers. And so after I implemented this, I got lots of results. And so I'm just going to kind of go through them one by one. And so the goal points are what are called 1G mergers, which are two black holes that are first generation that merge. And these two black holes are directly from dying stars. And then the purple points are 2G and 2G black hole mergers, which are mergers that happened from black holes that have previously merged and then are merging again. And then the red points are just 3G and higher. So these are black holes that have merged at least 3 times or more. And so as you're increasing in these generations, you're also increasing in mass because you're merging two black holes together. And so this graph you can see is the kick velocity of the black hole remnants before the surrogate was added in. So this is just the default version of MCFACS. And this is plotted across the disk radius. And so as you can see, we have these distinct populations of the 1G, 2G, and 3G mergers that have kick velocities of about 100 kilometers a second. And so when we add in the surrogate model, the 2G and 3G mergers actually go down in their kick velocities. They decrease and almost in an order of magnitude. And so this is essentially telling us that whenever we add in numerical relativity for these black hole mergers, they weren't previously leaving the disk whenever they merged, but they're even more so not leaving the disk because of their decrease in kick velocities. And so one of the other parameters that we were unexpectedly finding to upgrade was actually the spins of the black holes. And so this is showing the final remnant spin of the black hole across the kick velocity. And as you can see here, there's a wide sweep of final spins for the higher generation mergers. And so what we ended up doing was comparing this to the surrogate model, which I'll get to in a second. But we compared it to the surrogate model by resetting these 2G and 3G mergers just to some general points that we were anticipating that these spins would be at. And then we also added in another simple analytical model that was very similar to the full surrogate model. And so the full surrogate model is the complete most physically accurate representation of these black hole spins. And as you can see, as we're increasing in spin, we're also increasing in mass. So the spins are changing drastically when we add in the numerical surrogate, but also we're seeing that higher generation mergers gives us higher spins for the remnants. And so these objects are also merging in the disk for the default model in these three little populations. But as we add in the surrogate model, we can see that they're actually not changing that much. And so that tells us that even though the surrogate model is more computationally efficient, it's still very expensive to run. And so we can use the precession model, a cheaper analytical version, to run these spin and kick velocity calculations, but they won't change where the populations are ending up in the disk. And so by upgrading this for McFACS, we have a great idea of what is physically accurate for these populations. And so that means we can use McFACS for simulating intermediate mass black hole mergers inside of AGN disks. And AGN disks are now a more possible environment for these objects to form in, which are also detectable by the upcoming LISA mission. And so these intermediate mass black holes and black hole mergers in AGN disks will be detected hopefully by LISA and are a very promising source of gravitational wave detections. Thank you.
Thank you so very much, Sean Ray. Let's see if we have any questions in the comments. All right, so now we will once again thank you for your presentation. We will go to our last presenter, Melanie Santiago.
Hello, just making sure you can hear first.
Yep, we can hear you. Go ahead and
Okay,
share your
perfect.
screen.
Yes. Wait, let me.
We can see it.
Okay. Okay, perfect. Thank you so much. All right. Hi, everyone. My name is Melanie Santiago. I just finished my first year, so I guess I'm a second year PhD student at the University of California, San Diego. And today I'll be presenting work in collaboration with Lieke van Zon in the Netherlands at the Radboud Institute, and my research advisor at UC San Diego, Floor Brook-Garden. And today I'll be talking to you about the metals of the cosmos, unified enrichment from double white dwarfs and neutron star mergers. And just to start off, to motivate this work, I just want to take everyone back to reminding themselves of when they feel energized, when they feel tired, what they're made of, what the universe is made of, and how that's all connected. You might be like, those are very disconnected, but I would argue that they are actually really connected, and that is from the elements that we are made of and control the way that we live our lives, and what is composed of us and the universe around us. Something in particular that I like to say I have in common with maybe chemists, although I'm definitely not a chemist, are my interests in how these elements are formed. And so in my work, I primarily look at the origin of elements formed from two different types of events, so white dwarf or type 1a supernova and these merging neutron stars. And like I said, you might have various interests in why you care about these elements, including like your own body and what it's made of, but also for astronomers, maybe metallicity, the evolution of metallicity throughout time, and the enrichment of the universe in general. But in honor of the World Cup and sports-like things, I wanted to give you examples of just how important these elements can be. For example, we have the Olympic medalists here that are made from these events. So to like be more specific, we have copper, silver, and gold that are made from these two events. So if you're not convinced that they're important and that they create cool elements that we care about, then here's another sports related reason why you could care about that. In order to actually understand the enrichment and these elements that appear in this periodic table, let's actually deep dive into these two explosive events that actually produce these elements. So let's go through toy schematics of how to create these two events that then enrich our universe, and maybe get some motivation as to why we want to look at these two events in particular. So I'll start with the Type 1a supernova case, and to remind ourselves, a Type 1a supernova, we think, is theorized to be produced from an exploding white dwarf that hits some critical mass. And this white dwarf is not going to explode on its own, so we often invoke binary evolution or binary system of two stars to explain how this Type 1a supernova, how this white dwarf can explode. And so in its evolution, the two stars might transfer mass from each other, and this transfer mass might be unstable. And by that, I mean the environment of the companion star will engulf the white dwarf. So they have the shared common envelope, shared common environment we refer to as common envelope. As this binary continues to evolve, this energy their orbital energy might dissipate in the form of unbinding this envelope. So you can imagine as they're interacting with the envelope and encountering some dynamical drag, the two remnants or stars within the envelope will orbit each other, and this orbital energy can be transferred to unbinding the envelope to get these two stars or two remnants that are now closer together. These closer together remnants are now able to efficiently eject energy in the form of gravitational waves, where they can eventually get closer and closer together until they merge to produce this explosive event, to produce some of the elements that we see today, like one of the Olympic medalists, copper. Now let's go on to the binary neutron star case, where we might see some parallels. So similarly, let's start in this binary system where we have this neutron star, this remnant of a higher mass star, that undergoes some mass transfer with its companion. And again, if it undergoes this unstable mass transfer, it'll get enveloped in this shared envelope with its companion, or common envelope, as we referred it to. And with a few extra steps, it'll get to a similar place where it's in this configuration where, because of its interactions within the envelope, it is able to get closer after the envelope is ejected. So you're left with this binary neutron star state that eventually, again, is able to efficiently get closer and closer together until it merges and produces the other types of elements we care about in our universe. So the other Olympic medalist, as an example. And so from this like detailed, maybe overwhelming picture of both of these events, I think the key takeaway here is that we get this enrichment of our universe of these different types of metals from both of these events, and they both also happen to have this shared stage, this shared common envelope stage. So what we want to do is ask ourselves if we can investigate this stage to understand how both of these events eventually occur and enrich our universe. So we can do just that. We can look at this common envelope evolution stage. And again, these two stars are, when they're in this common envelope, initially at some fixed separation, A initial, we'll say, and after it's ejected due to, like, again, the orbital energy being used to expel this envelope, at some final separation, A final, much closer together. In literature, this is often modeled as some energy budget. This is the only equation I'll show, but this energy budget, where this EM is the energy of the envelope. This, in parentheses, is this change in orbital energy that's causing this envelope to be expelled. And this alpha parameter is this efficiency parameter that's used to tell us, okay, how much of this orbital energy is being used to expel this envelope. So you could imagine, to get some intuition on this alpha, because it's important for my studies later, if you have an alpha equals 1, then you would say your orbital change in orbital energy is 100% efficient at unbinding your envelope so that you can get closer, so that you can get your state of these two stars that are close together that will eventually merge. Whereas if your alpha is equal to 2, let's say, then that almost sounds unphysical. You have a 200% efficiency at at using your orbital energy to unbind the envelope. But actually, that means that if this alpha is 2, it's encoding some uncertainty in this formalism where alpha is 2 is saying you need some other energy source that's making your process even more efficient at ejecting the envelope. But regardless of that, this alpha will affect, in general, our rate of how often these systems will merge and then enrich our universe. Because you can imagine different values of alpha will give us different final separations, which will give us different rates at how often they merge now. So we can use this parameterization and this common envelope evolution as a way to understand the two events we just talked about that enrich our universe. And so how do I actually do that? Well, I can evolve isolated stellar binaries. Someone mentioned Cosmic before. I use COMPAS, which is a similar tool where we just populate a universe with binaries, evolve them through time, compute how often these systems merge to then enrich our universe. And then for different simulations, change alpha, which tells us, which then gives us some merger rate with this alpha that we can then use to compare to observations. So we're essentially seeing what value of alpha, what treatment of this common envelope stage will give us realistic rates when we compare to observations. And so some very, very preliminary results are, I will show now, where this x-axis is this efficiency parameter, just to remind ourselves. And this y-axis you can just think of as like the merger rate, how often these things merge and then explode. And so now this might seem like a lot, but I'll try to break it down briefly. These solid lines are just the results that I get from my simulation of simulating these binaries and then having them merge. Specifically, the lines with stars connected are everything, some subpopulations that represent the type 1a supernova population in our binary. And then the purple line connected with dots is the binary neutron star mergers from our simulation. And like I said, our interest is comparing these to observations as well. So the shaded regions are our observational constraints, where the shaded purple region is for specifically binary neutron stars, and the shaded blue region is for the type 1a supernova rates. And the main takeaway, there's a lot on this plot, but the main takeaway of this is just to say that at these lower alpha rates, alpha efficiency values, you can see the change in the merger rate is changing with the same order of magnitude for these white dwarf or type 1a supernova as they are for the neutron star case, which makes sense because you would expect that they share common envelope evolution. So if you change something about that, they would change the rate for each of these different events similarly. But we see in these higher alpha values that that's not the case. At these higher alpha values, the rate is changing at different orders of magnitude. So that tells us that this alpha and common envelope in general should be treated very differently amongst these different events because they're changing at these different orders of magnitude. Essentially, common envelope evolution is very distinct and different amongst these neutron stars and white dwarf populations. And so we can't just use one fixed global value for alpha to describe all of these systems. And just one last takeaway is in my study, I was looking at one shared phase between two explosive events that enrich our universe, binary neutron star mergers and white dwarf supernova or type 1a supernova. And we found that especially at high alpha values, these common envelope parameters cannot be treated the same amongst these two different types of events, which helps us understand how we can adjust our simulations to then accurately model the universe and model how we enrich our universe. Thank you, and I'm excited for any questions.
Thank you so much, Melanie. So we're at time, but to be fair, we have time for one question if anybody has one question.
Okay.
Okay. Well, if there aren't any questions, thank you to all of our presenters. Thank you so much for all of these talks across a wide variety of areas of astrophysics. This is really enjoyable for me. And yeah, we'll be in touch. Thank you so much for presenting. I hope everyone learned something, and hope everyone's enjoying Black Space Week so far. Thank you all.